Good morning to everyone present here. My name is Hussain and I'm a BTech final year aeronautical student, and my co-partner is Mr. K. Dinesh. So we are going to present our project. The title of our project is Design and Model Analysis of Bulkhead of an Aeroplane Fuselage. So our internal guide is Mr. M. Raja Gurunathan and our external guide is Mr. Ramaswamy. So the main objective of our project is the evolution of different geometrical configuration of the bulkhead through stress analysis and normal mode analysis approach. So in this project, what we are going to use is that we had already used CATIA V5 R18 for designing purpose, and for finding the model analysis and stress analysis we had used NASTRAN, PATRAN and software. So in this some key points are there that should be noted for everyone. So that key points are transport aircraft, fuselage, pressure bulkhead, internal pressurization, finite element method and stress analysis. So the important part of this project is introduction. So in the introduction, aircraft structure is the most obvious example. As we know everyone, the structural efficiency result in lightweight and high operating stress. An efficient structure must have three primary attributes, namely the ability to perform its intent function. So here are some types of force are acting on this fuselage. That force due to cabin pressurization can be considered as one of the critical load cases for the fuselage structure. So as we know, fuselage everyone know. So I am going to explain the type of loads acting on that fuselage. So the fuselage will experience a wide range of load from a number of sources. The weight of the fuselage structure and payload will cause the fuselage to bend downward from its supporting at the wing, putting the top in the tension and the bottom in compression. The fuselage that loads include thrust from the engine propelling the aircraft, and that lift generated from the wings, and drag generated by the aircraft structure engine moves through the air, and some internal pressures due to cabin pressurization. So we everyone aware of that cabin pressurization is there. Cabin pressure is there. It's the property to for the safe purpose of the pilot and the passengers who are sitting inside the aircraft. So at that time, sometime what happened in that cabin, that oxygen quantity has been minimized. For that the safety purpose of their passengers and that pilot, we need a normal cabin pressurization inside the aircraft, so that everyone can survive easily. So there are some standard atmospheric charts which will be common in every aircraft. So there will be some altitude and some pressure. So that altitude is what? That altitude is that we can explain is that the maximum height from the ground to the flight is flying. So we can call it that altitude. So some at sea level 2000, if the altitude is 2000, and at that time pressure is 14.7 bar. Okay, so this one is the main diagram of the fuselage is bulkhead. So that in bulkhead, a bulkhead is a structural member of the aircraft fuselage, of which a typical fuselage has a series from the nose to the impingement. So the primary purpose of bulkhead is the establishment the shape of the fuselage and reduce the column length of stringers to prevent instability. So we had already designed this bulkhead in software, that CATIA software. So as we know that in CATIA only that a designing purpose we can draw, and that pressure bulkhead. So what is pressure bulkhead? Pressure bulkhead is that on that bulkhead two types of loads are acting on the bulkhead. So one that load we can call as pressure bulkhead. That pressure bulkhead is what? From in atmosphere from outside to some loads are acting. Some loads are acting naturally. That load we can say as pressure load. So it will create some problem in that bulkhead. So as to reduce that problem, we are using some members including Z section and C section and L section. and material used for the construction of bulkhead. So the major points of this project is material. So before going to do some experiment on that project, we need to know that material, about that material, which material we have to choose. So for that we had chosen that aluminum alloy, because in most of the aviation industry, this aluminum alloy is more strength and more reliability. So this aluminum alloy is also cheaper as compared to different metal. So this aluminum alloy, so completely 50% of that aircraft is made up of aluminum alloy. So nowadays some aircraft are made up of composite material. So yeah, nowadays in that aircraft also we are using, in that controlling surface we are using that composite material. Okay, so this aluminum alloy we are using aluminum alloy 2024T3. Okay, so there are some series of this aluminum alloy like 2XXX series, and that ultimate strength we should know. Ultimate strength, everyone aware of the ultimate strength. That ultimate strength is that the complete total maximum load carrying material. After that the material will convert into plastic or it will fall down. Okay, so load calculation. So how we can calculate the load acting on the aircraft? So for that we should know some altitude of the aircraft. That altitude is 8,000 altitude. The pressure level inside the fuselage decreases with cause abnormalities in the body condition of the passenger. So for maintaining the atmospheric pressure level inside the fuselage, internal pressurization is given. Here the pressure variations start from 6.5 psi to 9 psi was considered, and for each increase in pressure the analysis of pressure bulkhead carries out using the NASTRAN software. So load calculation for the fuselage. How we can calculate the total load acting on the fuselage? So the load acting on the fuselage by its self weight is 1000, passenger weight plus luggage plus cargo is 400, the total weight acting on the structure is 1400, and the UDL is everyone knows that uniform distributed load is equal to the total load divided by 3.14 radius of the fuselage. So total, after calculating everything, we are getting UDL as 2.4148 kg/mm. So design process. How we are going to design this project. So this complete structure of this project. First, what we will do in that CATIA software, we are going to design that project, and before that we should know the dimensions and the material properties, everything. Before starting that project we should know everything. So for that we are having some specific dimensions for every parts, like for bulkhead we are having some dimensions, for stringers and for longerons and for frames. Every parts including in this project we are having separate dimensions. So if the dimension will vary here to there, so we can't exactly make that project properly. So for our aim was that only. So what we had done before going to do this project, we just had a glance in some previous international papers and some FAA we should know. So that designing methodology in this we had used computer-aided design. Is the use of the computer system to assist in the creation, modification, analysis or application of a design. So CAD software is used to increase the productivity of the design, improve the quality of design, improve communication through documentation, and to create the data base for manufacturing. So what is the advantage of this CAD software? So we should know about this one. So to increase, first it will increase the productivity, and second improve quality of the design, and to create data base for manufacturing. So this one, you can see the side view of mid-fuselage bulkhead in the side view. So there are loads of bulkhead. We are a side view of bulkhead. We have to mention here. So there is side view, and there is top view, and there is front view. So if you will see from side view, you can see the total, how many windows are there, how many longerons and stringers are there in that bulkhead. You can easily see from side view. If we are going to isometric view of this bulkhead, we can see inside. We can see what are the things inside in this bulkhead, and the overall area of that bulkhead we can see in this isometric view. So what happens is, so procedure involved in stress analysis is the general procedure of FEM. FEM, everyone knows that finite element analysis. It's a part of that stress structure analysis. So in this, what we are going to do is, first we are importing that model or creating the model. So after that, what we will do, discretization of the structure. Means discretization means what? Meshing of the structure. We will mesh that after importing that model in that CATIA software. We will in that NASTRAN PATRAN software, we will mesh that material. So after that meshing, after we are going to create that material. Okay, after that we are applying 1D 2D and 3D properties. So applying load and boundary condition after that. So after the analysis, after the solver, after the result, these are all the steps which comes under the NASTRAN PATRAN software. This one we have to follow for completion of our project. So in that bulkhead, some important model and creating the model, I already explained you in that previous slide. So there are some side view and front view of important models, and side view, important model for side view. After drawing this bulkhead in CATIA, so after that we are going to draw this, we are going to mesh, and we are going to find the how many stress it is carrying and how many model analysis we have to find. So for that we are first we are going to see the model imported side view of that diagram. So you can easily see in this side view, we can see what are the things in front of that diagram bulkhead. You can see in this side view, and that isometric view I already explained you. In that we can see the overall structure of the bulkhead. So you can see this. So discretization of the structure. So this one already I explained you, discretization. So some areas are there, some error in quad elements are aspect ratio worm, taper, screw. Okay, so here number of elements. So in elements we had used bar and quad elements. In number of elements in bar we had used 3, 6, 1, 2, and in quad we use 9, 7, 6, 0. In position in bar, that is bulkhead, and in position in quad, so that is skin. So this is the mesh solid material of our whole bulkhead. After completion, or after calculating that how much load it's carrying, and that how much diameter it needs, and everything, completion of everything. So then after that we will get a solid mesh model. So we are having load of 2000 kg applied equally over the side, one side of the wing we have uploaded. So in this you can load and boundary condition. This diagram you can see the one side of the bulkhead is totally fixed, so that is boundary condition. So here all of the 6 degree of freedom. So in this 6 degree of freedom, every degree of degree of freedom is fixed, and the load is acting on the bulkhead. So that load is actually acting on the bulkhead. So the linear static analysis, maximum principal stress analysis. In this diagram you can easily determine the maximum principal stress at bulkhead is 138 Newton per mm square. So in this principal stress at bulkhead, So maximum shear stress load, you can easily find where is the maximum stress, where is the maximum stress value, and where is the minimum stress value. You can easily find here already. So the maximum stress value at bulkhead is 204 Newton per mm square. This one is warm missile stress. In this warm missile stress is nothing but you can see easily where is the warm missile stress, the maximum. So you can easily find the warm missile stress at bulkhead is 380 Newton per mm square. So this one is displacement. So in this displacement you can see how much the maximum the bulkhead will displace. So from a particular point is 35.1 mm. So result validation, after that everything is completed, and after that we have to calculate. So after that we have to get some result, and the result validation is done based on material ultimate strength with RF table. RF means reserve factor. RF is equal to ultimate strength by octane stress. So if RF value is less than 1 means component fail. If RF value is greater than 1 to 1.5 means component is safe. If RF value is greater than 1.5 means component is too safe. So in here that RF rear pressure bulkhead, here are some values obtained from that previous diagram. So type of we know type of stresses and ultimate stresses, octane stress, and RF and displacement value. So for one basis I already told you that ultimate stress is 483 and octane stress is 380, RF is 1.27 and displacement is 35.1. And for maximum principal stress, the ultimate stress is 483 and octane stress is 138 and RF value is 3.5 and displacement is 35.1. And for maximum shear stress is for ultimate stress is 289.8 and octane stress is 204 and RF value is 1.4 and displacement is 35.1. So after that look at can easily see where there are 6 mode of normal analysis. Is one mode is axial. In this axial what happened, the material will move explained axially. So in we are having axial animation. You can see this animation easily. You can see how many number of frames and how many scale are there, maximum and minimum stress analysis you can see here, and deformation also you can see here. So here one is bending. So how you can see how this bulkhead is bending from its central point. So it will bend like if you were applying some load on that material, it will bend. So like that only. So you can see for at the time of bending where is the maximum bending, and where is the minimum bending. For that you can easily find here. And this one is bending animation. You can see bending animation. See how it's bending. So you can from this you can find that maximum and minimum bending. So this one is fourth one is twisting only. Twisting means what it will do. Twist in this twist, it will twist from both sides. It will twist. So in this maximum, you can see the maximum minimum value, and that deformation also you can see where the deforming, and this twisting and twisting animation. So axial, there are 6 modes of normal modes. So conclusion from everything, after concluding everything, the mid-section bulkhead has been designed for aircraft operating load involving the best industrial standard and following the FAR regulation. So the stress concentration in bulkhead, maximum pressure load in different kind of mode shaped by this project we found. Our stress concentration area is the bulkhead and maximum load carrying capacity of bulkhead. So the 3D model of the bracket have designed an analysis to check the behavior of the model under static loading condition, and that has been found out. So the project has future scope of the load acting on a aircraft mid-section bulkhead and most vulnerabilities and time depend on 6 degrees of freedom. There we can carry our fatigue dynamic test for accepting it for final applicability of bracket for real-time use in the aircraft. So there are some reference book which we had reference while doing our project. So there are some Peter CATS is there for stress analysis, and for aircraft structure TGS Maxon is there, and for fuselage design Robert Young NASA is there. Thank you to everyone. I hope you like our project.